And did everybody find this slide then? It's kind of in the middle of part 7. So today we're just going to finish up part 7 and we're going to call it a day. And then that means then Monday and Wednesday I'll have to figure what I want to do. Monday I'll probably kind of go back and talk a little bit about heat and energy. And then Wednesday we might start new material. I don't know. Okay. So density is basically, if you need to calculate the density of anything, the symbol for density is that Greek letter rho. Looks kind of like a P. If you need to calculate the density of anything, all you got to do is, like you did in lab, take a thing and get the thing's volume and get the thing's mass and do a division, and you have the density. And you guys, when you did your rubber stopper, you got the density of the stopper in terms of, let's see, that would have been units of grams per milliliter, and you got the density of the block, and that was grams per centimeter cubed. Now, we're going to actually use the density now as a physical property of something as a conversion factor, using the factor label method. If you ever want to know what you can accomplish with regard to density, for instance, look at the units. So here in a minute, I'm going to try to convince you, and we're going to do a few problems. If you have density, you can go from grams to milliliters. If you have density, you can go from milliliters to grams, okay? That's kind of how it is. If you have density, you can go from grams to centimeters cubed. If you have density, you can go from centimeters cubed to grams. So if you look at the units, you know how you can use it. So density, what we say is the conversion factor. Using the factor label method like you guys are doing for your homework, we're going to basically use it as a ratio. Insert it so our units cancel. That's it. Jessica. Hey. So we're kind of middle of part 7, density again. Okay. So we're going to work a few problems with the same substance. So somebody went to the lab and they got the density of methanol, and they told you it's 0.792 grams per mil. Now the next slide, actually, I call it unpacking. The next slide kind of takes this 0.792 grams per mil and it unpacks it so you can plug it into a factor label problem. The 20 degrees Celsius, it's important, but you're not going to use it in your problem. So let's look at what the two problems are. The first problem is, if we were going to diagram it, we would say, what is the mass? So I'd put over here on the right side, question mark grams. What is the mass of 242 milliliters? That's how I would kind of diagram the first one. The second one is, what is the volume? So question mark volume. And I'll go ahead and says it once in milliliters of 50.0 grams. So I want you to kind of be thinking that when we work these, the thing that we're trying to convert is going to be our first term over 1. Then we're going to use density to get, in the first case, from milliliters grams. In the next case, we're going to use density to get from, as our second term, to get from grams to milliliters. So that's kind of what we have going on here. So like I said, unpack that 0.792 G/ml. I should really never see you use that just like that in a factor label problem. So if we unpack it, this is what I mean by unpacking it. What that means is for methanol, it's a physical property of methanol. In 1 milliliter, or 0.792 grams would occupy 1 milliliter. Now, the flip is true. For methanol, we could also say that 1 milliliter would weigh 0.792 grams, just for methanol. We could also flatten it out for methanol. We could actually say, I know it sounds weird, that grams are equal to milliliters, but for methanol, 0.792 grams is equal to 1 milliliter. Now there is uncertainty in that 0.792, so actually we're going to have to, there's 3 sig figs, we're going to have to, that will guide how we round if it's the shortest number. Okay, so let's do the first one. So the first one, the first term is going to be 242 milliliters over 1. So again, if we want units of milliliters to cancel, we want to be left with units of grams. Do you see where we're just going to use density straight up? Okay, if we plug in density for methanol, as our second term, 0.792 grams over 1 milliliter. Notice that units of milliliter cancel, and we're left with units of grams. Units of milliliters cancel. I would usually put this over 1. We're left with units of grams. Notice that there was uncertainty in actually the volume, but there's 3 sig figs. There was also uncertainty in the 0.792. Okay, also 3 sig figs. We're allowed 3 sig figs. Does that work for you? And actually, in yesterday's lab, this is exactly what we did to get the mass of our 25.0 milliliters of water. We put 25.0 milliliters over 1 and then use the density of water. Okay, so for the second one, our starting term is going to be that 50.0 grams over 1. Now in this case, if we want grams to cancel, we're going to have to use the reciprocal or the flipped of the density. So we're going to put 1 milliliter over 0.792 grams. And then we got it going on. So in that case, units of grams will cancel. We're left with units of milliliters, which is perfect. All right. 3 significant figures seem reasonable? Okay. So 63.1 milliliters. That's it. So if you ever want to know what you can use density as a conversion factor for, look at the units of density and it kind of guides you to what you can use it for. Since units of density are grams per milliliter, or grams per volume, you can go back and forth between mass and volume, just like this. All right. So let's do another one. Now this takes it up a couple of notches. Okay. It looks so innocent, right? But, so what mass, so I put that over there on the right, question mark mass, but it says I want mass in pounds. What mass in pounds is 0.875 cubic inches? You're like, what? Well, anything, any length cubed like that is volume. Okay, so actually the density in this case is given as in grams per milliliter. So grams per milliliter. So basically, do you guys see that milliliter is volume? Basically, we have to fix our volumes so they agree. And then we can go ahead and use density, but it's kind of frustrating because we can use density to get to grams after we get to milliliters for volume, and then we got to fix our mass to get from grams to pounds. So I have here kind of diagrammed one way to probably go about this. So we said if you ever have something like this English units cubed, and you need to get to metric volume, which is milliliters, you're going to go through centimeters. So we can go from inches cubed to centimeters cubed using that relationship you're supposed to memorize. 1 inch is exactly equal to 2.54 centimeters. We could cube that. And then we could go to cute little milliliters, recognizing that the relationship between centimeters cubed and milliliters is 1 to 1. At that point, we can go ahead and insert our density. The density is 1.4 grams per milliliter. That means for this substance, 1.4 grams is equal to 1 milliliter. So that will be our link to mass. Now we're not quite done yet because we want it in pounds, drat. So we need to, and you don't have to memorize this one. This is an approximate relationship. 1 pound is approximately equal to 453.6 grams. Voila! So let's string them up. The first term is going to be the thing we want to convert. 0.875 inches cubed over 1. And then we could put 2.54 centimeters over 1 inch. We could put that 3 times, which is probably what I would do. Or you could just put it quantity raised to the 3rd power. Either way. The beauty here of either way is that now our inches cubed have canceled. We're left with centimeters cubed. Now we're ready to go to milliliters. So we put 1 milliliter over 1 cubic centimeter. Now we're ready to introduce density. Let our milliliters cancel. So we want grams in the top, milliliters in the bottom. So we're going to go ahead and use what I call kind of the straight up density. 1.4 grams over 1 milliliter. So everything's canceled except for grams. One last thing to get it to pounds, we're going to use this relationship up here that you do not have to memorize but brings some uncertainty. We're going to put units of grams in the bottom, units of pounds in the top. So 1 pound over 1 pound over 453.6 grams. Cool. Like I told you, one of my favorite things is canceling. So centimeters cubed cancels, inches cubed cancel, centimeters cubed cancel, milliliters cancel, grams cancel, and we're left with units of pounds. Whew. So I bet you guys buy this. I have 3 sig figs here. There's no uncertainty brought by that second term, no uncertainty brought there. I only have 2 sig figs here, and actually there is uncertainty brought by this, but I have 4 sig figs. So we're looking at 2 sig figs. So 2 sig figs, remember that as you write this, this 0 is just a placeholder, and there's your 2 sig figs. Whew. I would not put one like that on the test. That'd be no fun. No fun for you to do, no fun for me to grade. But it could be homework. Okay? All right. So these will be due on Monday. Let's take a look at these. Let's see. For this first one, this is kind of like the problem that we just did. Basically, the density is given, and they are asking in A, you're supposed to go from, says what is the mass? So question mark grams, and you're going to start with 387 milliliters. And to accomplish that, you are going to use this relationship. 1.11 grams is equal to 1 centimeter cubed. But it looks like we got to insert, now that I'm looking, this looks like we got to convert milliliters to centimeters cubed first. And then B, what volume in liters? So we're going to put question mark liters on the right, and we're starting with 3.46 kilograms. So similar kind of, we got to fix our kilograms to grams, and then we can do grams to we can do grams to milliliters using density, and we can do milliliters to liters using the relationship of 1,000 milliliters is equal to 1 liter. So this is the one where you use density. Okay, another one. This is a little clever. Basically, this is a kind of a, I say stupid, a thief that's not very bright. Basically, it's kind of like you guys remember, like, what was the Raiders of the Lost Ark, where the guy went and I think it was like an opening scene where he took a bag of sand and was going to replace it with the gold that he was trying to take. But the problem is that gold is a lot denser than sand. Okay. So they give you the density of gold and sand. It was the same volume though. So basically, think of it this way. We have, here's my bags, here's my 2 bags, ugly looking bags that a thief would take. and this is AU as in gold, and this is sand. They both have a volume of 1.75 liters. And then the background information tells you that the density of gold is 19.3 grams per centimeter cubed, and the density of sand is 3.00 grams per centimeter cubed. And the thing is it's all about weight sensitive. So you're supposed to, for A, calculate the mass. So you're going to go from volume, you're going to use volume, you're going to have to go what? From liters to milliliters, and then from milliliters to cubic centimeters, and then you can use your density to get to mass. You're going to do that for both of them. So mass of AU and mass of sand. That's A. And then B says, basically, did he pull it off? Okay, so you probably, do you think he pulled it off? No. I think he probably died right there. Or the trap went off. Okay. So those two are due on Monday. So let's go ahead and finish up. Now we're going again back to the lab 2 weeks ago. The egg lab, where you did the weight percent shell, weight percent white, and weight percent yolk. So we're going to use that as a conversion factor. So you guys calculated them, but now we're going to use it as a tool. So I said anytime somebody gives you a weight percent, if you need to unpack it, which we're going to have to do, okay, if they give you a weight percent, it's the mass in grams of the thing per 100 grams of the mixture that the thing is in. That's how you unpack it. So let's work a problem. Somebody made a sugar solution, and they made it 7.2% by weight sucrose. And we're going to use that as a conversion factor to work these next two problems. So for problem number 1, okay, it says how many grams of sucrose. So question mark grams of sucrose are there in 65 grams of solution. 65 grams, SOL apostrophe N is my solution. And I'm going to show you how we can actually use weight percent to do that. The second one is what is the mass of solution? So question mark grams solution goes over there on the right of 3.3 grams of sucrose. We're going to use weight percent. All right. So I should never grade a problem, or you should never turn in stuff that leaves it as the percent sign. You should always unpack that percent sign. So 7.2% by weight sucrose means 7.2 grams of sucrose in 100 grams of the mixture, which in this case is the whole solution. So 7.2 grams of sucrose. Think of it this way, that, let's see, we could actually calculate the grams of water in there, couldn't we, if we had to? The grams of water, since it's only got sucrose and water, would be, what, 100 minus 7.2. Okay, but this is the water and the sucrose. All right, so we can use it that way in our problem. We can use the reciprocal or the flip in our problem, or we can flatten it out and use it on our problem. The weight percent of sucrose in a solution is just how they made it up. Remember, the cool thing about solutions or mixtures is the author of the mixture gets to kind of be creative and make it up how he or she needs to. But we could also say in 100 grams of solution, you would have 7.2 grams of sucrose. We could also flatten it out. That's a physical property of that particular solution. So I do a lot of unpacking. When I look at a problem right off the bat, I kind of write in the margins what that means. Okay, so just a little bit of caution when we're dealing with, when we're trying to get our units to cancel. Be careful that in some cases you have grams are not necessarily, you have to be what we call explicit. Remember the other day I talked about an explicit decimal where you like hardcore put it in there? That's an explicit decimal. You have to be explicit with regard to your labeling, be as specific as possible. Okay, so let's work them. The first term is going to be 65 grams of solution over 1. And if you look back a couple of slides ago, if we want grams of solution to cancel, then we're going to go with that first one at the top, right? We're going to go with the 7.2 grams of sucrose over 100 grams of solution. So our units of grams of solution cancel. And we're left with grams of sucrose, and that's it. We're done. So remember that if you're unpacking, oftentimes kind of what's in the denominator, in this case grams of solution, there's no uncertainty brought by that 100. But there is uncertainty brought by the 7.2. So we have 2 significant figures there, 2 significant figures there. Grams of solution cancel. So around the 2 significant figures, I got 4.7 grams of sucrose. To me, this is almost a visual thing. It basically says if you have 65 grams of the solution and you use heat to boil off all of the water, you're going to end up with 4.7 grams of sucrose. So the next one, the first term is going to be 3.3 grams of sucrose over 1. And in this case, if we want grams of sucrose to cancel, we're going to use the reciprocal or the flipped version. So it's going to look like 100 grams of solution over 7.2 grams of sucrose. So grams of sucrose cancel, we're left with grams of solution. Again, it looks like only 2 significant figures. So 46 grams of solution. Not bad. Okay. So yeah, we're back to 13 again. You guys did a weight percent problem. Here's what these look like. So both of these sets will be due on Monday. So this one, they are all sucrose solutions. Okay. So for instance, for A, it says, and by the way, they are all sucrose solutions, and you're supposed to determine the amount. So for all of these, it's going to be question mark grams of sucrose. For all of them. So like for instance, and they'll have a very similar pattern. So for the first one, I would start with 48 grams of solution, SOL''N, and to do that, the thing that's different for each of them, it looks like, is the solution concentration. So for this one, 3.7%, that means, I'll go ahead and do the flattened out version, that means that there are 3.7 grams of sucrose equals 100 grams of solution. Now that is going to be different for all of them because they all have varying weight percents. So that's kind of A, similar pattern. Now I noticed for B and C, it's kind of mixed up a little bit because B, you're going to have to convert milligrams to grams first, right? And C, you're going to have to convert kilograms to grams first on the front end. All right, this next one, this is of the 3, this is the hardest one, I think, but you should do fine. It talks about a silver nitrate solution, and it gives us what is the maximum amount of silver in grams that can be played out with 4.8 liters of silver nitrate solution. And it gives us the property of that silver nitrate solution. So let me go ahead and kind of draw a picture. So here's our silver nitrate solution, AgNO3, AQ. And I'm going to go ahead and I'm going to give it a volume. They go ahead and they say you got a big old tub of that, 4.8 liters of that. and they go ahead and they say that particular solution, okay, there are 3.4 grams of pure AgNO3 per 100 grams of solution. The last bit you need to work this problem is very important. They say that the density of the solution is 1.01. I'm going to put 1 point, anytime you have density of a solution, it's grams of the solution, SOLN, per 1 milliliter of the solution. Now this is a good example where I kind of look at these as puzzle pieces. I look at the weight percent as a puzzle piece, the density as a puzzle piece. I try to kind of get students, steer you guys towards, can you see the thing that's kind of specific to this problem actually is the volume. That's actually going to be my first term. Like, okay, so that's going to be your first term. Well, where then? If I put 4.8 liters over 1, where then? Well, look at your puzzle pieces. 4.8 liters over 1. I'll go ahead and 4 liters solution. Of my puzzle pieces, do I have anything that has volume of solution? Yes. That's how I work these. So the next thing that I can use is actually my density. Go ahead and do density. But I can't use it right off the bat because density has milliliters and the denominator instead of liters, so I'm going to have to fix that first. Well, once I get, just kind of use your imagination. If I fix liters to milliliters, I go ahead and insert density. I have milliliters down there. Then I have grams of solution. Well, what would I do then next? If I'm carrying a grams of solution in the numerator is my only term, notice if I stick this one there, I can get grams of solution to cancel. So actually kind of the way I'm thinking, and there's always, there's different ways, orders you can use because it would all kind of come out in the long run. So if I go ahead and stick that in there, notice I'm going to get grams of AgNO3. And I know this says, and I think by chapter 13 we've talked about another concept we haven't talked about yet. So where it says, what is the maximum amount of silver, okay, I just want you to say what is the maximum amount of AgNO3. Okay, I don't want you to go, because at that point, if you're kind of tagging along with me, what would units you'd be left with are grams of AgNO3. Perfect. Okay. There's actually one way to kind of massage out the mass of the Ag from the AgNO3, but we're going to kind of stop there for now. Okay? So your answer, this is an odd problem, so your answer will be different than the answer in the back of the book. All right. Last one isn't as bad. Now instead of silver nitrate, it's sodium chloride. Okay, so it kind of goes back to me, something like we've been working at before. What is the mass of ocean water? So, of course, the ocean water is the mixture. So, basically, grams of solution, okay, if you have 45.3 grams of NaCl. And actually, you guys should just be able to accomplish that just using the 3.5 grams of NaCl per 100 grams of solution. So, any questions about all those? Okay. Well, that's as far as I wanted to get today. So, have a good weekend. I do check my email if you have any kind of questions throughout the weekend. Cool.